Melamine is an organic base and a trimer of cyanamide, with a 1,3,5 skeleton. Like cyanamide, it contains 67% nitrogen by mass and, if mixed with resins, has fire retardant properties due to its release of nitrogen gas when burned or charred, and has several other industrial uses. Melamine is also a metabolite of cyromazine, a pesticide. It is formed in the body of mammals that have ingested cyromazine. It has been reported that cyromazine can also be converted to melamine in plants. Melamine combines with cyanuric acid and related compounds to form melamine cyanurate and related crystal structures, which have been implicated as contaminants or biomarkers in Chinese protein adulterations. Etymology: the German word Melamine was coined by combining the words Melamine and Melamine is, therefore, unrelated etymologically to the root mellus, from which the words melanin, a pigment, and melatonin, a hormone, are formed. Uses: melamine is combined with formaldehyde to produce melamine resin, a very durable thermosetting plastic used in formica, melamine dinnerware, laminate flooring and dry erase boards. Melamine foam is used as insulation, soundproofing material and in polymeric cleaning products, such as magic eraser. Melamine is one of the major components in pigment yellow 150, a colorant in inks and plastics. Melamine also enters the fabrication of melamine polysulfonate used as superplasticizer for making high-resistance concrete. Sulfonated melamine formaldehyde is a polymer used as cement admixture to reduce the water content in concrete while increasing the fluidity and the workability of the mix during its handling and pouring. It results in concrete with a lower porosity and a higher mechanical strength, exhibiting an improved resistance to aggressive environments and a longer lifetime. The use of melamine as fertilizer for crops had been envisaged during the 1950s and 1960s because of its high nitrogen content. However, melamine is much more expensive to produce than are other common nitrogen fertilizers, such as urea. To be effective as a fertilizer, it is essential that the plant nutrients are released or made available in a manner that matches the needs of the growing crop. The nitrogen mineralization process for melamine is extremely slow, making this product both economically and scientifically impractical for use as a fertilizer. Melamine and its salts are used as fire-retardant additives in paints, plastics, and paper. Melamine derivatives of arsenical drugs are potentially important in the treatment of African trypanosomiasis. Melamine use as non-protein nitrogen for cattle was described in a 1958 patent. In 1978, however, a study concluded that melamine may not be an acceptable non-protein end source for ruminants, because its hydrolysis in cattle is slower and less complete than other nitrogen sources such as cottonseed meal and urea. Melamine is sometimes illegally added to food products in order to increase the apparent protein content. Standard tests, such as the Kjeldal and UMAR tests, estimate protein levels by measuring the nitrogen content, so they can be misled by adding nitrogen-rich compounds such as melamine. There is an instrument developed by the company CEM Corporation that allows the determination of protein content directly in some applications. This cannot be fooled by adding melamine in the sample. Melamine is also used as a nitrogen and carbon source for n-doped carbon nanotube. NCNTs can be prepared via chemical vapor deposition method by pyrolyzing melamine under an atmosphere in a horizontal glass tube. A thin film of iron is first deposited on a CCO2 wafer. NCNT synthesis occurs at a furnace temperatures between 800 and 980 degrees Celsius. Toxicity: melamine is described as harmful if swallowed, inhaled or absorbed through the skin. Chronic exposure may cause cancer or reproductive damage. Eye, skin and respiratory irritant. However, the short-term lethal dose is on a par with common table salt with an LD50 of more than 3 grams per kilogram of body weight. U.S. Food and Drug Administration scientists explained that when melamine and cyanuric acid are absorbed into the bloodstream, they concentrate and interact in the urine-filled renal tubules, then crystallize and form large numbers of round, yellow crystals, which in turn block and damage the renal cells that line the tubes, causing the kidneys to malfunction. the European Union set a standard for acceptable human consumption of melamine at 0.2 mg per kg of body mass. Canada declared a limit of 0.35 mg and the US FDA's limit was put at 0.063 mg daily. The World Health Organization's Food Safety Director estimated that the amount of melamine a person could stand per day without incurring a bigger health risk, the tolerable daily intake, was 0.2 mg per kg of body mass. Toxicity of melamine can be moderated by intestinal microbes. In culture, Coagulata regina, which rarely colonizes mammalian intestines, was shown to convert melamine to cyanuric acid directly. Rats colonized by Coagulata regina showed greater melamine-induced kidney damage compared to those not colonized. Acute toxicity. Melamine is reported to have an oral LD50 of 30–48 mg per kilogram based on rat data. It is also an irritant when inhaled or in contact with the skin or eyes. The reported dermal LD50 is greater than 1000 mg per kilogram for rabbits. A study by USSR researchers in the 1980s suggested that melamine cyanurate, commonly used as a fire retardant, could be more toxic than either melamine or cyanuric acid alone. For rats and mice, the reported LD50 from melamine cyanurate was 4.1 grams per kilogram and 3.5 grams per kilogram, compared to 6.0 and 4.3 grams per kilogram for melamine and 7.7 and 3.4 grams per kilogram for cyanuric acid, respectively. A toxicology study in animals conducted after recalls of contaminated pet food concluded that the combination of melamine and cyanuric acid in diet does lead to acute renal failure in cats. A 2008 study produced similar experimental results in rats and characterized the melamine and cyanuric acid in contaminated pet food from the 2007 outbreak. A 2010 study from Lanzhou University attributed renal failure in humans to uric acid stone accumulation after ingestion of melamine, resulting in a rapid aggregation of metabolites such as cyanuric acid diamide and cyanuric acid. Chronic toxicity. Ingestion of melamine may lead to reproductive damage, or bladder or kidney stones, which can lead to bladder cancer. A study in 1953 reported that dogs fed 3% melamine for a year had the following changes in their urine: reduced specific gravity, increased output, melamine crystalluria, and protein and occult blood. A survey commissioned by the American Association of Veterinary Laboratory Diagnosticians suggested that crystals formed in the kidneys when melamine combined with cyanuric acid don't dissolve easily. They go away slowly, if at all, so there is the potential for chronic toxicity. Treatment of urolithiasis. Fast diagnosis and treatment of acute obstructive urolithiasis may prevent the development of acute renal failure. Urine alkalinization and stone liberalization have been reported to be the most effective treatments in humans. Regulation in food and feed. The United Nations Food Standards Body, Codex Alimentarius Commission, has set the maximum amount of melamine allowed in powdered infant formula to 1 mg per kilogram and the amount of the chemical allowed in other foods and animal feed to 2.5 mg per kilogram. While not legally binding, the levels allow countries to ban importation of products with excessive levels of melamine. Synthesis. Melamine was first synthesized by the German chemist Justus von Liebig in 1834. In early production, first calcium cyanamide is converted into dicyandiamide, then heated above its melting temperature to produce melamine. However, today most industrial manufacturers use urea in the following reaction to produce melamine: 62COC3H6N6 plus 6NH3 plus 3CO2. It can be understood as two steps. First, urea decomposes into cyanic acid and ammonia in an endothermic reaction, NH2, 2COHCNO plus NH3. Then, cyanic acid polymerizes to form cyanuric acid, which condenses with the liberated ammonia, forming melamine, which releases water, which then reacts with cyanic acid present, which helps to drive the reaction, generating carbon dioxide and ammonia. 6HCNO plus 3NH3 C3H6N6 plus 3CO2 plus 3NH3. The second reaction is exothermic, but the overall process is endothermic. The above reaction can be carried out by either of two methods, catalyzed gas phase production or high-pressure liquid phase production. In one method, molten urea is introduced onto a fluidized bed with catalyst for reaction. Hot ammonia gas is also present to fluidize the bed and inhibit deionization. The effluent then is cooled. Ammonia and carbon dioxide in the off-gas are separated from the melamine-containing slurry. The slurry is further concentrated and crystallized to yield melamine. Major manufacturers and licensors such as Arasom Construction Industries, BASF, and Technica have developed some proprietary methods. The off-gas contains large amounts of ammonia. Therefore, melamine production is often integrated into urea production, which uses ammonia as feedstock. Crystallization and washing of melamine generates a considerable amount of wastewater, which is a pollutant if discharged directly into the environment. The wastewater may be concentrated into a solid for easier disposal. The solid may contain approximately 70% melamine, 23% oxytriazines, 0.7% polycondensates. In the Technica process, however, there is no solid waste and the contaminants are decomposed to ammonia and carbon dioxide and sent as off-gas to the upstream urea plant. Accordingly, the wastewater can be recycled to the melamine plant itself or used as clean cooling water makeup. Production in mainland China. Between the late 1990s and early 2000s, both consumption and production of melamine grew considerably in mainland China. By early 2006, melamine production in mainland China is reported to be in serious surplus. Between 2002 and 2007, while the global melamine price remained stable, a steep increase in the price of urea has reduced the profitability of melamine manufacturing. Currently, China is the world's largest exporter of melamine, while its domestic consumption still grows by 10% per year. However, reduced profit has already caused other joint melamine ventures to be postponed there. Surplus melamine has been an adulterant for feedstock and milk in mainland China for several years now because it can make diluted or poor quality material appear to be higher in protein content by elevating the total nitrogen content detected by some simple protein tests. Actions taken in 2008 by the government of China has reduced the practice of adulteration, with the goal of eliminating it. Court trials began in December 2008 for 6 people linked to the scandal and ended in January 2009 with 2 of the convicts being sentenced to death and executed. Melamine poisoning by tainted food. Melamine has been involved in several food recalls after the discovery of severe kidney damage to children and pets poisoned by melamine adulterated food. 2007 animal feed recalls. In 2007, a pet food recall was initiated by Menu Foods and other pet food manufacturers who had found their products had been contaminated and caused serious illnesses or deaths in some of the animals that had eaten them. In March 2007, the U.S. Food and Drug Administration reported finding white granular melamine in the pet food, in samples of white granular wheat gluten imported from a single source in China, in biologic technology as well as in crystalline form in the kidneys and in urine of affected animals. Further vegetable protein imported from China was later implicated. In April 2007, the New York Times reported that the addition of melamine scrap into fish and livestock feed to give the false appearance of a higher level of protein was an open secret in many parts of mainland China, reporting that this melamine scrap was being produced by at least one plant processing coal into melamine. 4 days later, the New York Times reported that, despite the widely reported ban on melamine use in vegetable proteins in mainland China, at least some chemical manufacturers continued to report selling it for use in animal feed and in products for human consumption. Li Xuping, a manager at Henan Xingxiang Yuaxing Chemical in Henan Province, stated, "Our chemical products are mostly used for additives, not for animal feed. Melamine is mainly used in the chemical industry, but it can also be used in making cakes." Shandong Mingshui Great Chemical Group, the company reported by the New York Times as producing melamine from coal, produces and sells both urea and melamine but does not list melamine resin as a product. Another recall incident in 2007 involved melamine, which had been purposely added as a binder to fish and livestock feed manufactured in the United States. This was traced to suppliers in Ohio and Colorado. 2008 Chinese Outbreak. In September 2008, several companies, including Nestlé Copyright, were implicated in a scandal involving milk and infant formula which had been adulterated with melamine, leading to kidney stones and other renal failure, especially among young children. By December 2008, nearly 300,000 people had become ill, with more than 50,000 infant hospitalizations and 6 infant deaths. In a study published in the New England Journal of Medicine, it was reported that melamine exposure increased the incidence of urinary tract stones by 7 times in children. Melamine may have been added to full government protein content tests after water was added to fraudulently dilute the milk. Because of melamine's high nitrogen content, it can cause the protein content of food to appear higher than the true value. Officials estimate that about 20% of the dairy companies tested in China sell products tainted with melamine. On January 22, 2009, 3 of those involved in the scandal were sentenced to death in a Chinese court. In October 2008, select fresh brown eggs imported to Hong Kong from the Hanwoo Group in Dalian in northeastern China, were found to be contaminated with nearly twice the legal limit of melamine. York Chow, the Health Secretary of Hong Kong, said he thought animal feeds might be the source of the contamination and announced that the Hong Kong Center for Food Safety would henceforward be testing all mainland Chinese pork, farmed fish, animal feed, chicken meat, eggs, and offal products for melamine. As of July 2010, Chinese authorities were still reporting some seizures of melamine-contaminated dairy product in some provinces, though it was unclear whether these new contaminations constituted wholly new adulterations or were the result of illegal reuse of material from the 2008 adulterations. On characterization and treatment of urinary stones in affected infants, the New England Journal of Medicine printed an editorial in March 2009, along with reports on cases from Beijing, Hong Kong and Taipei. Urinary calculi specimens were collected from 15 cases treated in Beijing and were analyzed as unknown objects for their components at Beijing Institute of Microchemistry using infrared spectroscopy, nuclear magnetic resonance, and high-performance liquid chromatography. The result of the analysis showed that the calculus was composed of melamine and uric acid, and the molecular ratio of uric acid to melamine was around 2:1. In a 2009 study of 683 children diagnosed in Beijing in 2008 with nephrolithiasis and 6,498 children without nephrolithiasis aged less than 3 years, investigators found that in children exposed to melamine levels less than 0.2 mg per kilogram per day, the risk for nephrolithiasis was 1.7 times higher than in those without melamine exposure, suggesting that the risk of melamine-induced nephrolithiasis in young children starts at a lower intake level than the levels recommended by the World Health Organization. In a study published in 2010, researchers from Beijing University studying ultrasound images of infants who fell ill in the 2008 contamination found that while most children in a rural Chinese area recovered, 12% still showed kidney abnormalities 6 months later. The potential for long-term complications after exposure to melamine remains a serious concern, the report said. Our results suggest a need for further follow-up of affected children to evaluate the possible long-term impact on health, including renal function. Another 2010 follow-up study from Lanzhou University attributed the uric acid stone accumulation after ingestion of melamine to a rapid degradation of metabolites such as cyanuric acid diamide and cyanuric acid and reported that urine alkalinization and stone liberalization were the most effective treatments. Testing in food. Until the 2007 pet food recalls, melamine had not routinely been monitored in food, except in the context of plastic safety or insecticide residue. This could be due to the previously assumed low toxicity of melamine, and the relatively expensive methods of detection. Following the deaths of children in China from powdered milk in 2008, the Joint Research Centre of the European Commission in Belgium set up a website about methods to detect melamine. In May 2009, the JRC published the results of a study that benchmarked the ability of labs around the world to accurately measure melamine in food. The study concluded that the majority of labs can effectively detect melamine in food. In October 2008, the U.S. Food and Drug Administration issued new methods for the analysis of melamine and cyanuric acid in infant formulations in the Laboratory Information Bulletin No. 4421. Similar recommendations have been issued by other authorities, like the Japanese Ministry of Health, Labor and Welfare, both based on liquid chromatography or mass spectrometry detection after hydrophilic interaction liquid chromatography separation. The existing methods for melamine determination using a triple-quadruple liquid chromatography or mass spectrometry after solid phase extraction are often complex and time-consuming. However, electrospray ionization methods coupled with mass spectrometry allow rapid and direct analysis of samples with complex matrices. The native liquid samples are directly ionized under ambient conditions in their original solution. In December 2008, two new fast and inexpensive methods for detecting melamine in liquids have been published online in the Chem. Journal of the Royal Society of Chemistry. Ultrasound-assisted extractive electrospray ionization mass spectrometry has been developed at ETH Zurich by Tsu et al. For a rapid detection of melamine in untreated food samples. Ultrasounds are used to nebulize the melamine-containing liquids into a fine spray. The spray is then ionized by extractive electrospray ionization and analyzed using tandem mass spectrometry. An analysis requires 30 seconds per sample. The limit of detection of melamine is a few nanograms of melamine per gram of milk. Huang et al. Have also developed at Purdue University a simpler instrumentation and a faster method by using a low-temperature plasma probe to ionize the samples. The major obstacles being solved, the ESI-MIS technique allows now high-throughput analysis of melamine traces in complex mixtures. The Mellah Manometer was a hypothetical design for a synthetic biology circuit, to used for detecting melamine and related chemical analogues such as cyanuric acid. The conceptual problem is hosted at OpenWetWare open source biology in collaboration with Diabio and has been discussed in various newspapers in the context of homebrew biotechnology. As of October 2009, the design has not been verified. Because melamine resin is often used in food packaging and tableware, melamine at ppm level in food and beverage has been reported due to migration from melamine-containing resins. Small amounts of melamine have also been reported in foodstuff as a metabolite product of cyromazine, an insecticide used on animals and crops. The Food Safety and Inspection Service of the United States Department of Agriculture provides a test method for analyzing cyromazine and melamine in animal tissues. In 2007, the FDA began using a high-performance liquid chromatography test to determine the melamine, amyline, amylide, and cyanuric acid contamination in food. Another procedure is based on surface-enhanced Raman spectroscopy. Member states of the European Union are required under Commission Decision 2008/EC to ensure that all composite products containing at least 15% of milk product, originating from China, are systematically tested before import into the community and that all such products which are shown to contain melamine in excess of 2.5 mg per kilogram are immediately destroyed. Melamine on metal surfaces. It is reported that melamine molecules adsorbed on ore 111, or Ag 111, surface tend to arrange into honeycomb or closed-packed structures. Such a self-assembly occurs due to the intermolecular hydrogen bond interaction. This ordering was further investigated using classical Monte Carlo and DFT calculations. See also, non-protein nitrogen, Leon High, references. External links, Melamine Materials Safety Data Sheet, OECD Screening Information Data Euroset, Melamine. FDA webpage with information on pet food recall. European Commission decision imposing special conditions governing the import of products containing milk or milk products originating from China. Statement on melamine from the International Fertilizer Industry Association, Toxicological and Health Aspects of Melamine and Cyanuric Acid, report of a WHO expert meeting in collaboration with FAO, Melmac Central's History on Melamine.